Hey, this is Sanyam Bhutani, and you're listening to Chai Time Data Science, a podcast for data science enthusiasts where I interview practitioners, researchers, and Kagglers about their journey, experience, and talk all things about data science. Hello and welcome to another episode of the Chai Time Data Science Show. In this episode, I interviewed Dr. Boris Dorado, a research scientist at CEA, where he's working on some very interesting projects in the domain of computational physics, which we talk all about during the interview. In this interview, we talk about Boris's first Kaggle competition predicting molecular property organized by Champs, where he teamed up with 4 Grandmasters, and the team was called 4 Grandmasters and the Brain, which landed a gold medal by finishing 8th on the competition. In this interview, we talk all about Boris's experience competing in a team with seasoned Kagglers. This was his first competition, as I mentioned. His takeaways from that, as well as his takeaways from working with the amazing Kagglers. I'd also like to thank people who submitted questions via the AMA section, and to Boris, who of course was kind enough to agree to it. For now, here's my interview with Dr. Boris Dorado. And I'd also like to mention, if you're interested in finding more about this Kaggle competition, next episode will be an interview with Andres Torubia, who's a seasoned Kaggler, and his team finished second in this competition. So stay tuned or subscribe for that. For now, here's the interview with Dr. Boris Dorado. Please enjoy the show. I'm really excited to have Dr. Boris Dorado on the show. Thank you so much for joining me and allowing the AMA section as well.
Yeah, thanks for inviting me. Thanks so much.
Sure thing. Pleasure to have you. So you hold a PhD in material science and you have a focus in computational physics and are currently working as a research scientist at CEA. Could you tell us, how did you get started with machine learning, and where did machine learning start to come into the picture of your research?
Yeah, so it started actually very, very recently. What I do at work is we're solving nonlinear differential equation numerically. And so we need a lot of power, a computational power to do that. And we kind of reached the limits of our current computational capability. Okay. And so we had to find another way to accelerate this calculation, to find alternative way of solving these equations. And one was machine learning, which was actually the focus on the computational, on the predicting molecular property challenge. Okay. So it started like this. Just try to go further in our solving the differential equations.
I'm sorry, what's the other way apart from machine learning? Is it like just scientific computation?
Sorry?
What's the alternative? Like, if you weren't using machine learning, it's just scientific computation, or how do you approach the problem otherwise?
Yeah, it's solving a numerically differential equation. So you have a big Schrödinger equation that we want to solve, okay. and we use iterative gradient descent procedures to find the solution of that. We don't actually solve the equation. We solve the equation, but not like finding the true solution analytically. We just use
a brute force of sorts?
Yeah, no, it's not a brute force. It's we're transforming the equation into a minimizing problem. So solving the equation is just like trying to minimize a big function with lots of variables. Okay. And so it takes a lot of time.
Got it. So you also followed a traditional path, if I may, in research. Could you tell us what made you pick physics as a career path and take up the research domain instead of the industry?
Actually, I wanted to do chemistry before that. So yeah, I was really interested in chemistry, and during my master's, my master's course, there was a lot of chemistry that we had to learn by heart, and I kind of didn't like that, so I switched to physics. But
Okay.
yeah, I've always been more. I can say, well, I would say that I'm doing physical chemistry. That's actually what I'm doing. I'm not doing really physics or
Okay.
chemistry. I'm doing physical chemistry,
Got it.
and yeah, that's why why did I choose? So I'm working in nuclear energy, and I choose this path not so much for nuclear energy, but rather because of actinide science.
Mhm.
So nuclear reactors are made of uranium and plutonium, and it was more the physics of actinide that was interesting me, like the radioactive decay and all the processes of radioactivity,
Right.
more than nuclear energy. So that's how I started into the path of nuclear
Got it.
energy.
So to me, it also sounded like you're working on some secret Iron Man reactor core. Could you tell us more about what current projects are you working on, and maybe share some secrets of your lab?
Sure, I won't be able to share some secrets, but
Okay.
we don't have any secrets. But we are developing reactor cores. That's for sure. I don't know if it's Iron Man. Maybe we are, but I'm not. Yeah, I'm not. Yeah, I don't have a high enough clearance to know that.
Okay.
But no, I'm working on nuclear reactors. So I've worked a lot on traditional pressurized reactor cores, which is oxides of actinide, so uranium oxide. So that's uranium and oxygen,
Okay.
and I'm interested in how they evolve during the reactor operation.
Hmm.
So you have your reactor cores, and it's burning, and it's emitting a lot of different atoms because it's radioactive, and so
Right.
and so it's transforming in a lot of different stuff, and it's emitting neutrons everywhere. And so I'm trying to figure out by using computational calculations and I'm trying to figure out how it's evolving in the reactor,
Okay.
if it's and how can we increase the efficiency and increase the security in case something happens.
Okay. So I can already see the trends, but once machine learning came into the picture of your research, did you find any parallels between physics and machine learning? Because both have this similar experimental setup where you have to run so many experiments, some work, some don't.
Yeah, definitely. There is definitely a parallel between machine learning and physics. That's wwhy it wasn't so hard for me to go into machine learning, because it's as you said, it's like they have the similar trend in terms of research. You're trying things, and they're not working, and so there is this cycle where you have an idea and you implement it, and then you see it doesn't work, and then you try to iterate over that. And the I was surprised that there's also a lot of all the algorithms are minimizing a cost function in machine learning,
Right.
and I realized that the machine learning community has had exactly the same problem as we had, trying to find the global minimum of a cost function, and
Mhm.
so there was metastable states where you couldn't find the global minimum, and so this is what I had also had problem. So there were a lot of parallels, and the takeaway from that is that I can I think that the machine learning community can benefit a lot from the physics community, and the other way around too. I took from the Kaggle competition, I took a lot of interesting ideas that I want to do in physics now.
Okay. So, do you think your maybe patience of working as a researcher where things fail, some don't work out, was helpful in this domain as well?
Sorry.
So, this patience that a researcher requires, that maybe you spend a few months on working on an idea and that doesn't work out. So, did you find that also helpful in machine learning, because
Yeah.
it's
Oh,
similar?
yeah. Yeah, that's definitely similar. Yeah. You're trying to find an idea, and so you're working. I would say that in physics, maybe uh, it's more of a brute force in machine learning. You have an idea, you implement it, and you try it, and it's since the calculation is quick, you can you can see very quickly if your idea works. In physics, it takes a little bit. The time scales are a bit more important, meaning that you have an idea, it takes some more time to implement it than just machine learning, and then to test it, it takes a few months. So I would say that maybe in physics you have to think just a bit beforehand. You have to think if your idea is going to work or not. You just can't implement everything that passes through your head, because it takes more time to validate it.
Got it. Because it's more of a physical world that you're working in, not just a computer, I would assume.
Yeah. There's physics behind it, so you can first think about it before trying to implement it.
Got it. So coming to the predicting molecular properties competition, congratulations on your first, actually it's a
Thanks.
team gold medal.
Yeah.
Was this your first Kaggle competition, or did you also have some casual competing experience before this?
No, that was really the first. The only competition that I had before that was it was not competitions, actually. It was a skill test during interview processes for new jobs.
Okay.
When I applied for new jobs, they asked me to this skills test where I had to predict prices for houses or for loaners or this kind of things. And
Right.
but no, that was really the first challenge that I ever signed up for.
That's amazing. Also, getting a first gold medal is, I'm sure, an amazing experience, which we'll just talk about. But
Yeah.
before that, could you help us set the stage of what was the challenge about, and how is it related, if it is, to your current research?
Mm-hmm. So the challenge was to try to predict properties, chemical properties, magnetic interactions between atoms in molecules.
Okay.
And this is actually very difficult to do with computational calculations. So the input data was what we call the QM9 data set, which is a very well-known benchmark data set in chemistry, in computational chemistry. And the QM9 dataset has a lot of different physical chemical properties, like the potential energy of the molecule, its vibrational frequencies when it's vibrating, and the band gap when you're exciting it. It takes some amount of energy to send electrons to different levels, and so they were giving you this kind of levels. So
Okay.
a lot of I would say usual properties, and the properties that we had to calculate in the challenge is actually very difficult
Okay.
to calculate. And so I was surprised that it was that the organizers had found a way to calculate these properties. And so it's no wonder that machine learning can be used to calculate these properties, because using computational solving the Schrödinger equations and finding these properties is very difficult.
Right.
And it's related to my research because the training set was so the training target was the target label was calculated in the training set using the same approximation that I use at work.
Okay.
I mean, I was very well aware of this calculation. I knew exactly what they had done, and so I was in I was in my environment.
In your element. Okay.
Yeah, I was in my element.
Got it. So once you found the competition and you thought this will be interesting and easy maybe for you, so what were your first go-to steps when you started working on the competition, and how did you decide to approach the problem when you initially started?
So I never told myself it would be easy. I was I knew that there were a lot of really good people on Kaggle, and so it was just like more of an experiment for me at first. I was like, okay, I know all the scientific part of it. I know about magnetic couplings between molecules. I know, so it will allow me to focus more on machine learning than in physics, because I won't have to struggle about physics. And my first approach was I wanted to try how, I've been learning machine learning on Coursera, and I wanted to my first thoughts were that I wanted to apply what I had learned on Coursera
Right.
onto the training set. So it was very, very elementary what I did. I really did what we were told on Coursera. So I
Okay.
started with my training set, and I split it in like 70% and 30% for training and validating. And I used really elementary machine learning algorithm like random forest and SVM and something like that. And then I realized it didn't well. It scored very, very. The score was very low compared to when I checked on the leaderboard. But and so I realized, okay, something's definitely is better than what I'm doing.
Mhm. And once you started getting the bite of Kaggle, could you tell us what was your high level approach in this competition, and how did you structure your workflow? I think this was also before you teamed up. So how were you competing before you teamed up with? I think first it was Andrew Lukianenko.
Yes. So the high level approach, I started with Andrew's kernels, and
Okay.
this was really, really interesting, and I really liked the guy. The first I as soon as I read his kernels, and it was very informative, and he was doing a lot of EDA, and it was fun to read his kernels, and I started to. First, I realized first that there were a lot of people in Kaggle that who were sharing stuff, and that I didn't know. And Andrew was sharing his own private algorithms to calculate, and so this is where I discovered about the cross validation, the k-fold cross validation,
Yeah.
and that was actually very much much more. Accurate than what I was doing with just my 70% and 30%. And I also found about light gradient boosting models, and this shifted my score really nicely, actually, because what I had devised a new input feature that was called ACSF, atom centered symmetry function,
Okay.
and it was not working very well on my decision trees. And when I used Andrew's kernels and Andrew's scripts of LGBM with this k-fold cross validation, it worked actually pretty well. And so this is where I thought, okay, maybe I should team up with Andrew because he seemed to have a lot of knowledge about machine learning, and I have a really great input feature that I can't use. So let's team up.
Interesting. You also written an amazing write-up about your competition experience and how you ended up teaming up with the Grandmasters. We'll have that linked in the description. Could you maybe confirm or deny, are Kaggle Grandmasters human beings, or have they transcended into an alternate reality?
No, they're not real. They are bots. There are bots and Google bots that no, they're actually pretty fun, and it was really so really first it was surprising for me because I wasn't expecting actually that Andrew accepted my invitation request. And it was really surprising because I know I know that there are a lot of people competing for the gold medal. I wasn't here for the gold medal. I was here because I wanted to learn machine learning initially, and so imagine you are a Kaggle master, grandmaster, and everything, and you have some guy who just joined Kaggle for just one competition, and he's asking to invite to it. So So I told Andrew, okay, Andrew, I have a super nice input features. It's called LCSF. I've made a kernel about it. It seems great, but I miss machine learning skills, and so I think we should team up because we are complementary. And I guess that's what worked. Maybe he thought that, okay, we need domain knowledge, obviously, in this competition. And in the end, we didn't, because the first, you have interviewed the second position and they have absolutely no domain knowledge.
Yeah.
And that's impressive. That's impressive. And so I guess that's why he accepted, because he knew that we needed domain knowledge. And the other grandmasters came after that, and yeah, it was very, very fun. And then I got to the Slack channel, and there are a lot of grandmasters there, and it's really nice to be part of this community, because they are, they're lifting up, they're lifting you to the top, because they know so much, and so you learn so much from them. It's really interesting.
A quick plug for the podcast. So we have the interview, the second position winners. That'll also be linked in the description, and an interview the Artgore and Lukanenko also. So please do check those out if you're interested.
Okay.
Could you maybe tell us how was this experience? Of course, you're an amazing learner because you picked up all these techniques right after you joined the competition. But how did teaming up with the grandmasters affect or maybe orient your learning approach versus how it was when you were just starting out?
Yeah, it was a hard task, because LGBM was okay. I mean, it was easy. It was just better decision trees and so on. So LGBM was okay. When we started thinking, okay, so after Andrew came, after we teamed up with Andrew, Phil came up. So
Right.
Silogram. Yeah, Silogram. Yeah, he joined the team, and so that was also a very nice surprise. And what's fun actually is that he actually had sent me an invitation request before I teamed up with Andrew.
Okay.
But I never seen it. I've never seen it, and I don't know what happened with Kaggle. Definitely, there was a problem, and
I think it's after you team up, so it doesn't show up anymore, if I remember correctly, on Kaggle.
Oh, because he was telling me that I've sent you an invitation, and now I see that you have teamed up with Andrew. So I don't know. Maybe the team invitation were sent simultaneously, and so something messed up. I don't know. And okay. And I was very naive about it. I remember because I received an email saying that the Kaggle team had to be answered. The Kaggle team request. He told me that the Kaggle team request had to be answered, and I was thinking, I thought that the Kaggle team, meaning the team of Kaggle, I thought that the team of Kaggle had asked me something, but I don't know what he was talking about, and so I answered him, but. Sorry, but what request are you talking about? I've never seen any email from the Kaggle team. And so, no, he told me, no, I asked you to team up with me. And I was like, come on, you're like the first, you're like almost the first guy on leaderboard. Why would you team up with me?
Right.
So yeah, he joined the team, and then Bojan joined as well. And then here we started thinking that we needed neural networks. And it's here that a lot of people in the team started to say, okay, now we have a problem, because there is absolutely no one in this team who knows about neural networks.
Right.
And so if it were only neural networks, it would have been okay. But it's not like the easy part of neural network. We had to go into graph neural networks, which are a derivative of recurrent neural networks. And then you have a lot of, you can plug convolutional and densely connected stuff. So it's like you're taking all the difficult stuff in the neural networks and you put them together. And this is what the competition was about. So yeah, that was actually very difficult to learn through that. And, but yeah, it was very interesting because I knew that I would need it for my work. So I got straight into it. And then I tried to learn about this interesting graph neural networks.
For context for the audience, when you actually Google graph neural networks, you find research papers, unlike CNN or RNN, where you'll find some courses, some articles nicely documented. So I think this was much of an open-ended question. Still, I think it still is at this time.
Yeah. And it's what I've noticed that so we Googled a lot of these graph neural networks, and it's also really flourishing field. There are a lot. There still are a lot of paper, but I think that's what deep learning is about. I think there is an architecture that pops out every day about. We have a lot of. This graph neural network. We have like 10 different versions of them, and each one is we will probably publish our solution, and that will make yet another graph neural network in this long list. I mean, everyone is changing something, and then it makes a better solution, and then up it's published. So we had a lot of Googling to do because there were a lot of different architecture out there.
Got it. So going back to your teaming up experience, you had this again diverse grandmaster team that you were with. And I think it also reflected in your activities. You had two amazing kernels from you that I'll have linked in the description. But could you maybe tell us how every grandmaster, because Boyan, for example, has a rich stacking experience. Christoph has a deep neural net experience. Andre is the king of EDA. So how did every one of these affect your process or your approach to?
So Andrew actually made a lot of EDA, but in this competition, EDA was not very interesting. It was just molecules, and between a molecule and molecule, that's always molecules. And so to me, Andre was more of he knew a lot about basic machine learning algorithm like LGBM, and so he was really efficient with this, and he had a lot of programming skills that were interesting for me. And definitely Phil Psilogram, definitely he was interesting. It was really interesting to work with him because I realized that, because I was wondering how can he get so high in the leaderboard by doing the same thing as we're doing LGBM. And so I realized that he had done really interesting features based on first on what was in the kernels, in the public kernels, but also how we could create these meta features, which I didn't know about, these meta features that like new features, and they absolutely didn't have any physical sense. I mean, he was just taking atoms and then first nearest neighbor, and then he was trying to build features that had absolutely no sense in physics. And I was surprised that it actually worked. I was like, how can this work? This has no physical meaning. Right. But yeah, it worked. And then Bojan is a master of stacking and ensembling. And
meme master also, unofficial meme grandmaster.
Yeah, true. The Slack channel, the meme master is really interesting. He's always posting something. Yeah, I agree with that. And so he helped a lot. That's always. If you ask someone else in the team, he will definitely tell you something else about these grandmasters and how they contributed to the competition. But this is really my feeling about this. And so Bojan definitely helped me understand what is ensembling, because I didn't know about that. I heard about that, but he was explaining me how he mixed all the blends that we had. So we were ensembling blends and blending of blends and blends. Right. And so it was really interesting, and I didn't know that, and I was surprised that it also worked. So then I looked on the internet for articles about ensembling, so I learned why statistically it works, and so that was really interesting for me. And then Christoph was maybe to me it was the more interesting, because he had so much knowledge of deep learning, and he had a PhD in mathematics. And so I do a lot of mathematics too, so it was really interesting to work with him. And he was coding, he was implementing all solutions so fast, and I had to keep up. So I had to work a lot to keep up with all these architectures, and no, it was really interesting. I think it was the most challenging for me was trying to follow up with Christoph. He's very clever guy.
Got it. So you also shared your hardware setup, which was pretty scary to me. It included multiple machines, multiple graphic card setups. Could you speak to how effectively did you use these, and to what extent were these helpful in your solution?
So I started with CPU. So I have a computer at work with something like 24 CPUs. So for LGBM, it was great. Yeah, it was great because it was going pretty fast, and I could run separate tasks and separate models, and it was nice. But when we came into neural networks, everybody told me, okay, we need GPU. And that's actually how I learned that we had GPU at CEA. And
Okay.
so I started contacting the IT team, and I asked them, okay, do we have CPU and GPUs? And they told me, yes, we do. We have a DGX. What's a DGX? It's a big machine with 8 GPUs, 8 P100s on that. So I didn't know what was P100 at that time. So I checked on the internet and I said, okay, looks nice. And then we have 20 V100s. But why is everybody, why is nobody using them? Yeah, because nobody's doing deep learning. Okay. Well, yet, because it was a prototype. It was a prototype machine. And so they were expecting that people were starting, will eventually start to do deep learning. And so they will be using them. So I started using them. The shame is that we couldn't efficiently parallelize the neural networks. So basically, the DGX is 8 GPUs that are on the same node. So the communication between them is very, very, very fast. But we couldn't take advantage of that because we couldn't find a way to efficiently parallelize them, the models. So this is what I'm going to try next. And so we're running different models on every single CPU. So that allowed us to do the hyperparameter search quicker, because we could run models separately on GPUs.
To reiterate for the audience again, JNN is an open research area. So unlike CNNs, which sometimes can be easily parallelized, this is where the trick or the open question would lie, I believe.
So, and sorry, but the problem also with GNN is that there is no framework for that. You know, if you want to do CNN or RNN with Keras,
GNN.
There's with Keras, you just put sequential convolutional pooling layers and recurrent layers, but we don't have for GNN. So you have to code yourself. You have to implement yourself the GNN. So that's why it's not parallelized as much as a convolutional or a recurrent neural network would be.
Got it. So what framework did you end up using, and how did you track your experiments across the team? I believe were they using the same framework or were it different approaches?
So we were using what Christoph used. So he was using PyTorch. So I went with PyTorch because I didn't know either Keras or PyTorch. So we went with PyTorch. So the other in the team were actually more of so Andrew were giving us papers, articles from the internet every day. So we would read them, and Christoph would implement them. And we went with PyTorch, and we went with it. We didn't code much, except when we had to. Christoph was doing most of the stuff, and we were changing. I mean, PyTorch or Keras, that's still very high-level programming language, and so we could just, even if we didn't know about PyTorch, we could just read the code and figure out that this is doing that and this is doing that. And so we could change manually hyperparameters or something without really modifying the code. So no, PyTorch or Keras was not much of a problem. I mean, we led this to Christoph, and then we would read what Christoph had implemented, and then we would change by hand the hyperparameters in that.
Got it. So there's a question from the AMA section by Tarun. He says, what did your testing pipeline look like when you were working on different ideas in parallel, I believe? And how did you keep a track of all these experiments and results?
So I don't know about the others, but the pipeline, the pipeline is easy. And that's the same in scientific research. If you want to have the influence of something, you make everything else constant in the calculation. And so this is the basic rule of trying new ideas. And so we were just, and sometimes when we change architectures, we had to make sure that everything else was staying constant. And so the graph that we were generating had to be the same. And so we had I had a big Excel file with all the architecture, all the possible graph, because the graph would change depending if we put this or that, and then the architecture, the interaction between the atoms and the bonds would change depending on the architecture. And so I had like a big Excel files with different hyperparameters, and I would keep track of the bet scores with this.
Got it. Another shameless plug by me is I'll have an article very soon up which will talk all about how to use open source tools to automate the part that you were talking about by building in callbacks into functions that will automatically create the spreadsheet for you instead of you manually tracking. So do check that out as well if you're interested. So I think Christoph mentioned that you tried a wild variety of ideas that did not work. Could you maybe tell us what ideas didn't work for you and some thoughts of why you expected them to work and maybe why they didn't work?
So to me, the ideas were more physical. I had a lot of physical chemistry input features that I was expecting to work, and it actually failed. And it was surprising for me because when I analyzed the problem, I was like, okay, we're missing this. So for LGBM, it worked great. For LGBM, because it's more interpretable than neural network. And so LGBM gives you at the end the input features. Yeah, that works the best. The most important input features. And so when I tried with LGBM new input features, depending on what was missing, that worked actually pretty well. But with neural network, it's more difficult. And so I was expecting things to work, and it actually didn't work. Like, the magnetic coupling between atoms is really related to what we call the magnetic shielding tensor. And this is what an input features that we had in the training set only, and not for the test set. So we first predicted the magnetic shielding tensor for the test set, and then we added to the training set, and it failed. And I didn't understand why. And so there's also I have a discussion topic on this on Kaggle. There was 8 different types of magnetic coupling to predict, and there were always 2 of them that had a very low scores compared to the others. And I was trying to find why we had a very low score. And so I plotted all the I drew all the molecules that had a very low score. And I realized that they had what is called mesomers, which is basically different molecule, the same molecule but with different properties. Okay. And so we didn't have this in our training data. And so I started adding mesomers to the training data, and it failed also. And but the problem is I still don't understand why. You see, it's strange that you're thinking that you are adding relevant information, physical and chemical information to the data for the neural network to work better, but it doesn't. And since it's so not interpretable, I still have no idea why it didn't work. But well, it didn't work.
Okay. If you could also maybe now provide I think it'll be too complex, but maybe a 50-foot overview of your solution, maybe from your point of view, that led to winning the gold medal, and the decision-making process behind what all models did you include in the final solution?
Yeah, so the final solution is a graph. So a graph neural network is actually a derivative of a recurrent neural network. It's just that you are updating through time. It's a deep recurrent neural network. Okay. And so we are adapted through time. The status of the atoms and the bonds between atoms. So it's going through time. That's why it's recurrent, and it's deep because you have one layer for each of the atoms, and so you have like a vertical layers for different atoms and bonds, and then you have horizontal layers for the recurrent through time process. And so that's a deep recurrent neural network, and the key thing is how you make. So first is the input features that you put to your nodes of your neural network, of your graph neural network, that are going to be updated. And so they are updated using each node, each atom is updated. The status of each atom is updated depending on its neighborhood and its own properties. And so we started with this, and basically, then you have to make to have atoms and bonds interact one with another.
Okay.
And so that's what define the main architectures of graph neural network. You have several different ways of doing that. And so we went with the SNET architecture. So we tried a lot of stuff, but our neural network was very deep, and so we had numerical problems. We have like exploding gradient issues, and we started doing dense connection between interaction blocks and everything in order to improve that. And in the end, what worked best was the SNET architecture. So we started from that. We modified it a bit in order to have more interactions between atoms and bonds, in order to remove the the exploding gradients issues. We had really dense connection between some of the layers, and then at the end, what we call a regression head that will calculate the properties you're looking for.
Got it. Okay. Now, maybe talking about, maybe in hindsight, how has Kaggle impacted what you're taking away into your professional life? Are you taking away any learnings that will help you in your quote unquote off Kaggle machine learning workflow?
Yeah, definitely. First, my LinkedIn profile exploded. I mean, because every one of the grandmasters in the team posted something on LinkedIn, and they have a lot of followers, and so you have all these people, they just come into your profile and then just click add friend. So I have like I don't know, maybe 50 to 60 connection requests every day.
Okay.
So it's a lot, and but that's actually you meet a lot of new people, and that's actually very interesting. And in my institution, they don't know much about Kaggle because
Right.
we don't do lots of machine learning. We're not doing lots of machine learning yet. So I don't have I don't have a lot of professional impact from that, except that if I want to change job, I think that it will help me a lot, because it means that I've been I think that you when you're winning a Kaggle competition, it means it's a lot, because it's the competition is very fierce. There are a lot of people, and it's really difficult to get in the top 15% in the top 15 people team. And I didn't realize this at the beginning, because this is my first competition, and I end up with a gold medal, and I thought, okay, well, why not? But talking with all the other members of the team, I realized that I got very lucky to be in this team with all these people and end up with a gold medal. And I had a lot of messages on LinkedIn telling me, "Oh, please team up with me next time." Okay. I wanted to say that, okay, I'm just a beginner. I got lucky in the first place. So no, I mean, I think that winning a gold solution in Kaggle, it also means that you have worked a lot during 3 months. And it talks. I think it tells a lot about your personality, whether you are someone who just give up on you are, I don't know, you have 200 or 300 at the leaderboard. Are you giving up, or are you still trying to make it to the top? And because it requires a lot of work. We've been working nonstop for 3 months, every weekend until late, and everyone was really available any time of the day, and during the weekend. So I think it also tells that you are willing to work a lot to find, to reach the top. And I think that's a nice thing to take out from this.
One of my favorite quotes is by Grandmaster Rohan Rao. He says, Kaggle is his favorite second dream job, but it comes at a sacrifice, I think, which you were just talking about.
Yeah, true.
So we were talking about people in your area. I think you're in the Paris area. So What is the machine learning scene there like? My question is based on the fact that people talk about, hey, I'm from India, we don't have a lot of grandmasters, or institutes here, do you think that's relevant? Or if you on Kaggle, that's irrelevant, you can team up with anyone who you probably don't know in real life as well?
So the ML scene in Paris, I have no idea.
Okay.
Yeah, I have no idea. I mean, since I'm so new in the machine, I know that we have a lot of startups and they are doing AI stuff, and most of them are not doing AI, but yeah,
Yeah.
they're thinking they're doing AI, but
Logistic regression.
yeah, a lot of this happens, and I don't know. I know that we're not using deep learning so much. Let's talk about France a bit.
Yeah.
We're not using deep learning so much. It's very because I think deep learning is uh, it takes time. It takes time, and so if you want to do it industrially, and if you want you write you write your neural network, and you want to how can I say that? Yeah, it's difficult because I mean, you work with commercial people and engineer people, and so you have to explain to them. They want to understand why this feature. They don't care about this or that feature, but they want to understand the model a bit. And so when you're talking to a commercial, you can't. They want something that's interpretable, and that's why decision trees or linear regression or polynomial regressions are used more than deep learning, because when your commercial guy comes and asks you, okay, explain to me this model, you can tell him, okay, this feature is more important because this coefficient in the regression is more important. And that's easier to say, okay, I have run like a deep graph neural network, and look, it's outputting a very well score, but I don't know what's happening. They don't want that. So I guess that the deep learning scene is very poor at the moment, but
Mhm.
I think that eventually it will increase. I know that in the United States, it's deep learning is flourishing. So eventually
Yeah.
we'll, and I know that Christoph have the same problem in Germany. Deep learning is not used very much in industry because it's not interpretable and it takes time. And so, yeah, I don't know if I'm answering the question, but
my
that's it.
my takeaway are what I actually wanted to ask was, if you're from an area that doesn't recognize these things, if you go to Kaggle, you can actually team up with people who might have the same experience, and you can also learn a lot by just going online to that platform.
Yeah, you can just learn a lot by just reading, and that's what I figure. First, you can learn a lot by just the public kernels, but it will bring you up to, let's say, not even bronze. I think you have to, after that you have to, so sometimes you have like one kernels that is leaking, and everyone just fork it, and then it
Yeah.
ends up in silver. But I thought first that it was it was I first thought that it was great to be in the 25% of Kaggle competitions, but then I realized that no, it wasn't, because everybody can be in the top 25% by just working just a bit.
Yep.
But and the takeaway is that if you really want to go silver or gold, you have to go well beyond what you're usually used to doing.
Right.
And because, for instance, for graph neural networks, if we there is no, like I said, there is no deep learning framework for that. There is no it's just you have for RNN or CNN, but not for GNN. And so if you're not willing to code yourself your own architecture and so look into it, then you don't go very, very far. And that's, yeah, so you can learn a lot. And maybe you can learn a lot from your work, because real life is not Kaggle competition. So you probably will learn a lot from all these people.
Yep.
But yeah, if you want to go up the leaderboard, it takes a lot of work and time.
For sure. Before we end the interview, I have one last question for you. What best advice do you have for someone who's just starting out, maybe on Kaggle and also machine learning, broadly speaking?
So just starting machine learning, I mean, I would say go on Kaggle, because I mean it can be a bit overwhelming at first, because I mean, nobody's using decision trees on Kaggle or something. They're all using LGBM or advanced stuff.
Yep.
But it will. There are always really nice kernels, and and even the Titanic stuff and the house predicting stuff is really great for EDA and stuff like that. So I learned a lot from that too. And I would say, yeah, go on Kaggle, try your competition if you have a bit of time. Just try to tackle the competition with very simple basic algorithms, so that you just realize how it scores compared to the others.
Right.
And then try to improve it bit by bit. Well, if you have the chance that I had to team up with Grandmasters, then go for it.
Got it. That's amazing advice. Thanks for that. Before we end the
Thank
call,
you.
what would be the best platforms to follow you and follow your work?
LinkedIn, definitely. I will post blog post on LinkedIn about future Kaggle competitions and maybe future works on machine learning. And I'm going to write something about graph neural network also, to try and like formalize everything that we've done during this competition and publish it eventually. So yeah, LinkedIn, definitely.
That's amazing. Really looking forward to those. We'll have your LinkedIn profile in the description. Will you be participating in more competitions in the future? Have you thought about that yet?
Yeah, I'm thinking about computer vision competitions. Okay. Because this is something that I want to be best at, and I know a bit about conv networks and all this stuff, but same as I said, I want to know to see how, if what I've learned on Coursera, for instance, is working great on Kaggle competition. So I would do exactly the same thing. I will go on a computer vision competition and try simple stuff to see how it performs, and then maybe get better.
Looking forward to your gold medals from there. Mm-hmm. And thanks so much, Boris, for doing this interview, and best wishes for your future competitions.
Thank you so much.
Thank you so much for listening to this episode. If you enjoyed the show, please be sure to give it a review, or feel free to shoot me a message. You can find all of the social media links in the description. If you like the show, please subscribe and tune in each week to Chai Time Data Science.